I can proceed now. We stopped at discussing the general structure of gravitational EFT, and I stopped at the moment that we eliminated all quadratic terms in 4 dimensions. Let me mention that this happens only in d equal to 4 exactly. In other dimensions, one quadratic term combination, Riemann square, is still there, and it's a non-trivial, non-vanishing contribution to the amplitude. Then how can we build the most general EFT Lagrangian? Which terms will be eliminated? In principle, at the level of Riemann cube, we also can immediately simply not write R cube, R mu nu cube in all combinations, and all terms containing R mu nu Riemann cube, Riemann squared. So all of these terms, we can simply forget about them and stay with R mu nu lambda rho cube contractions. That's the only thing which will be left at this order. But in addition to eliminating terms by equations of motion, we have also some nice relations like R mu nu rho sigma plus R mu rho sigma nu plus R mu sigma nu rho equal to 0, like symmetry properties of Riemann. And Bianchi identities for Riemann tensor, nabla alpha R mu nu rho sigma plus nabla rho R mu nu sigma alpha plus nabla sigma R mu nu alpha rho equal to 0. This also will reduce many terms like this. And in addition, we can express everything in terms of not Riemann tensor, but Wald tensor. Traceless combination of Riemann tensors, of Riemann tensor, C mu nu rho sigma, which is equal to R mu nu rho sigma minus G mu rho R sigma nu, and anti-symmetrized with respect to two indices here, minus G nu rho R sigma mu, anti-symmetrized again, plus 1/3 G mu rho G mu rho G sigma nu R. And we also have anti-symmetrization here. So Wald tensor is traceless, and for the Wald tensor, we have also up to 3 equations of motion. We have a nice property that d mu c mu nu rho sigma is equal to 0. And another important property is that box of Wald tensor, box of c mu nu rho sigma, is proportional to Wald tensor squared plus 3 equations of motion, which again are irrelevant. So it means that in EFT Lagrangian, once we see box of Wald tensor or box of Riemann tensor, because Riemann is again same as Wald tensor up to 3 equations of motion, we can say that instead of box acting on Wald tensor, we get Wald squared as a relevant contribution. Yeah.
Good relation. When the derivative of Wald tensor equal to 0, there is some anti-symmetry.
It's a contraction. Yes. Up to equations of motion.
Okay.
Not exact. Yes. These two nice equalities are up to equations of motion. Not exactly. Not always. This is exact. Definition of Wild tensor by subtracting that trace. So what are the knowing this, we can, for example, avoid writing terms which contain box Riemann, because we know it will be reduced to Riemann squared. Knowing this one, we also can avoid writing. Yeah, so we have only Wild tensor at this moment to have as a building block for EFT. But having Wild tensors, we cannot have. We immediately can eliminate terms where nabla is contracted to one of the indices of Wild tensor. So we have quite a limited number of combinations again. And in principle, all of these rules mean that the building blocks can be written as semi-nu rho sigma symmetrized covariant derivatives of Wild tensor. And if you have two derivatives, they also have to be symmetrized. mu1, mu2, c mu nu rho sigma. So all mu indices are symmetrized here. So this kind of objects are building blocks for the EFT. And in this moment, it is convenient to introduce to split Wild tensor to self-dual and anti-self-dual parts, like introduce CL and CR as 1/2 of C plus minus I C tilde, where C tilde mu nu rho sigma is equal to 1/2 epsilon mu nu alpha beta C alpha beta rho sigma. So we can define it with Levi-Civita tensor, like dual the combination which has Levi-Civita tensor, and this combination with plus sign will be self-dual, I think, and with minus sign it will be anti-self-dual with respect to multiplication by epsilon tensor. And this CL and CR will be independent, kind of independent building blocks. But one has to remember that if there is one epsilon tensor, then, for example, if there is only one epsilon tensor, then the term is parity violating. For example, this eliminates one of the, there are two combinations of Riemann cube, and one of them can be constructed with epsilon tensor, like epsilon mu nu alpha beta, Riemann, I think, alpha beta gamma delta are gamma delta epsilon psi are epsilon psi alpha beta. I'm not sure I'm doing everything correctly, but this construction is independent of simply contraction of three Riemanns without epsilon tensor. But this will be parity violating, or CP odd. So if we constrain ourselves with writing only CP even operators, we have only one Riemann cube combination. And then for simplicity, let's construct let me now just write what are the operators at the leading order of EFT of gravity. So in addition to Einstein-Hilbert term, we have A2 over lambda squared Gauss-Bonnet term. Yeah, let's write it. Let me write the general result in d dimensions. The construction, the way of constructing of these Lagrangians is described in the paper the general rules of construction of EFT can be found here. The Lagrangian for several operators, which I'll be using, and also the amplitude, these results are summarized here. So from this paper, let me simply write the result for first operators up to the ones suppressed by lambda to 8, by cutoff scale lambda to 8. So we have in d dimensions, we still have Gauss-Bonnet combination being non-trivial. Then the next term is Riemann cube. Only one combination for CP even theory. Then we have two combinations of Weyl tensor, what I call, I'll write lower what I mean by C squared. And another combination is a dual combination, C dual squared. Here I call C the quantity which is R mu nu lambda rho, R mu nu lambda rho. And C dual, I call it the combination with epsilon mu nu lambda rho, R lambda rho nu sigma, R nu sigma, also then nu mu nu, I guess. 1/2 is for being explicit. So we have one combination which contains normal Weyl tensors. And here we have two dual Weyl tensors, and we have two Levi-Civita symbols, which since there are two Levi-Civita symbols, it's still CP even term. And the next order is a bit more complicated. Up to lambda to 8, we have some new tensor with derivatives alpha alpha, C, and also we have the corresponding dual term lambda to where there are two terms with constructed with Levi-Civita tensor. And for tensor f alpha beta, what I introduce here, it's simply just derivatives of contraction of derivatives of Riemann. And Riemanns are contracted with indices with each other only. And dual f is a similar thing where I just put derivatives over there. just so that's the end of the story for lambda to 8 operators. So there are only two, but at the next order, there are 5 independent operators which are CP even over lambda to 10. I will not write all of them, but they are all explicitly written in this paper together with the corresponding amplitudes. So for the amplitudes, let me write it here, plus this combination gets multiplied by m to d mass Planck mass to d minus 2, and it will be there will be GR contribution plus minus 8 d minus 4 over d minus 2 a2 over lambda to 4 s cube minus 18 a3 squared s cube d minus 4 over d minus 2 s squared plus 2st plus 2t squared and there are also contributions from next order terms. They are a bit simpler. It's 8s to 4 over lambda to 6 a4 plus 4 over lambda to 8 a 5 plus s to 5. So in principle, this amplitude can have also some combinations containing for example, s cube tu, but it doesn't have it. It has only s to 5 and nothing else at this level. So there are some missing, returning to some questions I got, there are some missing constructions in the amplitude as it is, which doesn't correspond to any meaningful term in the gravitational action. So there is no complete one-to-one correspondence between the gravity, amplitude, and action. Some terms which one can in principle expect in the amplitude, they are missing. Then the next amplitudes are not zero. They also have some funny constructions like 12 over lambda to 4, 5 of a3 minus 2 d minus 4 over d minus 2 a2 squared. This is a combination x minus 2. This one is fully crossing symmetric. I define x as st plus tu plus su. 2 over lambda to 8. Some complicated dimensional dependent term a3 squared plus 10 a5 minus xy plus 16 over lambda to 6 a4 minus x squared. So a4 plus is equal to a4 plus a dual 4. So we see that only plus combinations with dual terms, they contribute to the first amplitude. And here we have contribution only to this amplitude for minus combinations. So here we have more or less all possible combinations in crossing symmetric amplitude, but apparently in this 4 pluses amplitude, we have only limited the number of terms, 6 over lambda to 4, a3y, plus something of order of lambda to 10 only, with a combination of y square. And we don't have any xy terms like this. There are none of them. So it's interesting to mention the structure that not all expected terms from the general not all general expectations about the amplitude symmetry are satisfied by something which can be obtained from EFT of general relativity.
Sorry.
Yes. In principle, you can expect, for example, here it's STU crossing symmetric amplitude. It could have, for example, XY contribution, but it doesn't. And you cannot adjust any term which will provide XY contribution in GR Lagrangian. So that's why I'm saying that the relation is a bit non-trivial here. In scalar field theory, it was much simpler, and normally it was you can adjust terms. You can make a one-to-one correspondence, but in gravity, there are some topological coincidences, like, for example, you will never get this term when d equal to 4, or here also don't have the term proportional to Gauss-Bonnet combination. Well, it is not clear. It looks like just you do the straightforward procedure of constructing EFT Lagrangian and computing amplitudes out of them, and you simply get some terms missing. Yeah.
By the first effective action from the corpuscular terms reaches where get energy momentum, and why is that cancelled or neglected?
It is neglected because we are considering now only the action which is relevant for scattering between gravitons only. So we consider only gravity part of the Lagrangian. In principle, we can also ask a question, how does it look like the action where there is no matter, only gravity, only gravitons? Yeah, if we are in vacuum, then we can simply say that it's zero. So here I plan to end the story about the EFT of gravity construction and switch to some formal things about scattering amplitudes. So the purpose of writing this kind of action is such that in principle we hope to obtain, we hope to assume that this theory works until some cutoff scale lambda, where here there is some UV completion, which we don't know precisely, but we expect some nice properties of this UV completion, and we want to derive the bounds on A2, A3, and so on, leading to some theory which has a good UV completion. That's the I will be moving to the story how to obtain bounds on these Wilson coefficients, following from certain assumptions, certain reasonable assumptions about the properties of UV completion, which is completely unknown, but of course we can assume some at least unitarity and some other good properties of QFT. For this reason, I need effective action, amplitudes, their precise form. I'm so much interested about poles, some analyticity properties of them. It's all very relevant for connection between ultraviolet and infrared theory, bounding infrared theory from assumption that it can have at all good UV completion. So the amplitude, we consider it as a function of S and T. But T can be also referred to, instead of T, we can also use the scattering angle, which is in one-to-one correspondence. This is for massless theory, and if theory is not mass, if we scatter if we scatter particles with equal masses, we get this kind of combination. The scattering angle will be equal to this. And now I will be talking about partial wave expansion. The amplitude as a function of scattering angle can be expanded in terms of eigenfunctions of momentum operator. In 4 dimensions, eigenfunctions of momentum operator are Legendre polynomials for scattering of scalar particles. So the expansion will look like so now we can express the amplitude as a function of S and scattering angle theta, and then with respect to this scattering angle, the amplitude can be written as a sum of Legendre polynomials accompanied with functions FL of S, which we call partial wave amplitudes. In fact, one can construct scattering of momentum of states not with of the states which are not the states of certain momentum, spatial momentum, but instead of that, consider scattering of partial waves, which are eigenfunctions of momentum operator, and then it will be described exactly as partial waves. The amplitudes of this scattering will be the partial waves, and this scattering will, this way we can get several properties of several unitarity requirements for these partial waves, that in each sector of momentum we must have unitarity for these partial waves. For example, one of the unitarity conditions is that imaginary part of each FL should be larger than 0. We also have optical theorem, and it leads to a bit more complicated unitarity condition. For partial waves, it can be written into, it can be obtained also in terms of partial waves. First of all, let me remember the expression of scattering cross-section. The standard textbook formula is 1/32 pi s integral over scattering angle cosine theta, modulus of A of S and theta squared. Then we can substitute the expression of the partial of the amplitude in terms of partial waves to the total cross section. And then I'll use the property of Legendre polynomials that the integral of such type, this part of the integral, will be just 2j plus 1 over 2 delta jk. So Legendre polynomials are orthogonal system of polynomials, and their integral with respect to angle will give will eliminate all of them. And due to that, we eventually get that the total cross-section can be expressed as a sum of partial wave amplitudes. Sum of modulus of partial wave amplitudes. I need it for the reason that I want to apply optical theorem to the whole amplitude. Luca mentioned that there is a relation between imaginary part of the amplitude and total cross-section. It can be also written in this way. I think any QFT textbook has it. So imaginary part of the scattering amplitude is equal to total cross-section. But let me also remind that total cross-section means total cross-section not only 2 to 2, but also the optical theorem is derived from kind of cutting diagram, which means that imaginary part of that will be very schematically sigma total of all of these processes, including multi-particle processes, which are not described by 2 to 2 scattering amplitude. For this reason, we have, when we come to partial waves, imaginary part is also described as sum of partial waves, 32 pi, sum of j plus 1/2 f imaginary part of fj of s pj of sine theta. Okay, here I already integrated it with Legendre polynomial, so I integrate both sides of this with Legendre polynomial, and I get for each partial wave. So I get just the sum, that imaginary part of partial wave is like this. And here, instead of equality, we get an inequality following from the optical theorem that sum of the partial waves is must be larger than this expression so this can be written not only for some, but also for each partial wave, which means that we can obtain that two imaginary part of each partial wave of S should be larger or equal to modulus of Fj of S squared with the factor S minus root S minus S minus 4m squared over S. So this inequality is very important in theory of scattering amplitudes. if we consider only 2-to-2 scattering, then we must have this inequality, and equality is happening only if we have no processes with where many particles are produced. But this bound is must be satisfied for all unitary series. So amplitude is not a random function of S and T in principle. It's a function which must satisfy sometimes very strict conditions to be an amplitude of some, at least here we assume only unitarity and only optical theorem. So this is like nonlinear partial wave unitarity constraint. And in addition, it also tells us that amplitude is in general is not an analytic function of S, for example, of S and T. It has non-analyticities. And if we scatter massive particles, we have, for example, if we consider forward amplitude, we have the following analytic structure. We have two branch cuts, starting one from 4m squared and one at 0. And if theory is good enough, which means that there is causality condition and we expect good properties of the scattering amplitudes, then the rest is a domain of analyticity of this amplitude. So it's analytic function in terms of an analytic function in S at fixed t going to 0. But the function in general, the amplitude cannot be analytic everywhere. It must have branch cuts, because otherwise we cannot satisfy this condition. If we have some tree-level scattering, it must still have some imaginary part related to appearance of this coupling in loops. So it must have non-analyticities. In addition, it can have poles corresponding to exchange diagrams. But if we are going away from real values of S and T parameters, we know that amplitude must be an analytic function, otherwise it leads to violation of Bogolyubov causality condition. But I don't have enough time to discuss reasons of that in much detail. So from here, let's treat it like an assumption that we have amplitude as an analytic function everywhere, except for branch cuts along only real axis. So until what time I have, can you remind? Until 6, okay. So already the properties which, the unitarity properties and partial wave expansion have certain implications for the behavior of the amplitudes at large values of S, at fixed values of T. Now I'll be working in the limit that T is much smaller than 4m squared in scattering of massive states. I'll consider it like a fixed parameter, so I'll not take exactly T to 0 limit. And S, I'm interested in the behavior of the amplitude at large S. The only tool I have at hand is partial wave expansion. Imagine I scatter scalar particles of mass m, and I have this kind of partial wave expansion. My purpose is to derive how fast can the scattering amplitude grow in this limit. S to some power, or I don't know what. In principle, my original assumption is that I'm working with some local theory which has a finite number of derivatives in the bare Lagrangian, and this assumption can be also treated as an assumption that my amplitude is polynomially bounded in both S and T variables everywhere. I have some power which bounds my amplitude. It doesn't have any exponential type singularities. It doesn't behave as exponent of S. It is bounded everywhere in the complex plane of both variables S and T. That's my assumption. From that, I want to derive so-called Martin-Froussard bound. Which is applicable for massive theory when T is fixed and relatively small. And it answers the question how amplitude behaves in this regime when S is large. And the answer is that A of S is less than S log squared S. So it cannot grow too fast. And I don't need to assume a lot to derive this result. Yeah, this result is of great importance for the further techniques, which is based on dispersion relations, where I will need to deform contours on the complex plane, including infinite circle. Once I have this bound, I can simply throw away all integration with enough suppression along the infinite circle, for example, and derive many implications of analyticity, which I'll do tomorrow. But now I need to derive this one. The derivations I saw in the literature were kind of not so clear to me for the reason that I never was understanding how one can guess what to do in order to derive this bound, having just partial wave expansion at hand. The purpose is to estimate the growth rate of this amplitude based on some analyticity assumptions that there is some domain of analyticity between 0 and 4m squared. But apparently, one can have a bound that, for example, FL of S modulus is less than 1. But it is not enough to compute something, because if I substitute, if I try to bound it by sum of PL with L plus 1/2, this one is just, this sum diverges. It's not convenient to make this. So I can, schematically, I can split this sum to L equal to 0 from where I can bound my partial waves by this condition. And also I need to estimate somehow the tail of the partial waves from some number L to infinity, where I need somewhat better estimate for partial waves, where they should be very, very small. And I need to derive how, somehow I need to derive that for large enough L, they are becoming very small in this case. In order to make this derivation, in principle, we can find partial waves out of amplitude. Since these Legendre polynomials are orthogonal, in principle, I can multiply everything by some other Legendre polynomial and locate my FL of S as some integral of, schematically, it will be some integral of A of S and theta with PL of cosine theta, d theta, d cosine theta. The problem is that I cannot really say something about this integral, because when L is large, PL behaves as cosine L theta approximately. So this is an oscillating function when L is going to infinity in this limit. And this is not suitable for making good estimate of partial waves at large L. Instead, there are somewhat better functions, which are known as Legendre functions Q. And one of the expressions, they can be expressed through Legendre polynomials. With this integral relation. But the nice property of these QL functions is that apparently at large L, QL of Z behaves as an exponentially suppressed function. Multiplied by some factor. But the main thing is that if I manage to derive, if I manage to express my partial waves through Legendre function of the type Q, I will be able to estimate large L behavior of this function. So let's try to do it. If I take an integral of amplitude, let's keep t of z function unknown for a while. I'll adjust it such that I get what I want. Let me contract the amplitude with this nice Legendre function Q, and hope that it helps me to obtain some expansion of partial waves. For now, I will also adjust what is the contour here. But here I just substitute instead of Qn its definition through Legendre polynomial. 1/2 integral from -1 to 1 p n of mu over z minus mu d mu. And now I want to change the order of integrations. I want to take an integral with respect to z. And I will achieve, after that, I will achieve some contraction of the amplitude with a Legendre polynomial. Yeah, here I can also express the function of, I can put the expression for the amplitude in terms of Legendre polynomials. So I keep 2L plus 1, I keep this integral, and I add f Lt of s, sum with respect to L. And PL will be a function of 1 plus T of mu over 2Q squared. And I define Q as a root of S minus 4m squared. So I got this expression, and in principle now I have a possibility to take an integral with respect to I can first take an integral with respect to the variable z. Here it's a variable z still. Since I have z minus mu and some contour, then if my contour is going around -1 and 1, this contour gamma in terms of z. I can, whatever the form of this contour is, it will reduce to the residue, which is located somewhere on this interval. That because mu is between -1 and 1, and z is somewhere here. So I just pick the pole. It's my z. So I take this integral by the use of residues method, and I get 2 pi I over 2 integral sum of 2L plus 1. I still have integral from -1 to 1 with respect to mu. I also have PL taken at the residue point, which is mu. So I get T of mu here over 2Q squared. And I divide it by, no, I'm not dividing it by something. I have FL of S in addition. So in order to reduce this sum with respect to L, now I have two Legendre polynomials, and I can use their orthogonality properties with respect to variable mu, but I need the other polynomial to be a function of mu, which means that I adjust the function t of mu such that 1 plus t of mu over 2q squared is equal to mu. And I know now from this condition, I know how t is related to mu here. Then I get just PL of mu. And for this integral, I know that it is simply proportional to delta NL. So I will reduce, there will be no integral at all after this. And then I'll just, will be left only with FL of S, which is expressed as 1 over 2 pi I, integral over this magic contour gamma, A of S, 2q squared, z minus 1. QL of z, dz. So now I can have a nice estimate of large partial waves because I know that QL is behaving exponentially. It's exponentially suppressed with large L. And if I have some boundedness properties of amplitude as bounded by S to N and something like this, I can say that for large enough L, my amplitude, my partial wave is bounded by exponent of minus root t over q, L plus 1/2 to be precise. It's some asymptotic expansion of Legendre function q. And here I get some traces of this expansion to L root t B0 of S, where B0 of S is my estimate of this function on this contour. It's less than S to power n, which I introduce like from the beginning. And then I need to find when I can start using this estimate proportional to exponent of, the main thing here is this exponent. It becomes better than estimate that FL is just less than 1 when L large is when basically we have exponent of minus root t over q L plus 1/2 root q over L root t B0 of S is equal to 1. From here, I find L, and L is equal to Q over 2 root T log Q over root T plus N Q over root T log S over 0. And then in total, it is proportional to, when S is large, it is proportional to root S log S. So I have to sum partial waves bounded by just 1 up to some number L, which is proportional, which is behaving like root S log S. And the tail will be exponentially suppressed with respect to L. So in total, the amplitude, the low spin contribution to the amplitude will be proportional to basically sum of PL of 1, because I consider small t 2L plus 1 sum with respect to L from L equal to 0 to L large. And this is proportional to L squared, because I just sum 2L plus 1 from 0 to some finite L. And exactly in this way, I get L squared, which is proportional to S log squared S. Exactly this way I got the Martin-Froissart bound. But I have also the large spin tail, but apparently due to exponential suppression of this large spin tail, I can estimate that it is a irrelevant combination. When S goes to zero, when S goes to infinity, it behaves as so a L larger than L is proportional to the estimate will give me S to N exponent of minus root T root S log S. And if I take S to infinity limit, even S to N factor, whatever N is suppressed compared to exponent. So in large S limit, I don't care about higher spin contribution to the partial waves. So that's the result which was obtained from the minimal number of assumptions, like some analyticity in a small domain, and also partial waves, partial wave expansion. We got quite a strong result that the amplitude cannot grow fast if the theory is if the overall amplitudes are polynomially bounded. And this doesn't depend on N, by the way. So this constraint doesn't depend on what power is bounding the overall amplitude. Okay. So I will make use of this result tomorrow very much. But let me also comment that this discussion is very much based on the fact that the amplitude is analytic around t to 0 and in some domain s between 0 and 4m squared. So there is some domain of analyticity. Unfortunately, if we deal with massless loops and massless scattering, there is a problem to repeat all this technique, because there will be contributions like log t, 1 over t, which break analyticity, and simply you cannot write, you cannot take a limit of small fixed t. There will be also, I had somewhere the analyticity domain at t equal to 0. So if it is a massive theory, then we have some range where it is analytic. But if the theory is massless, we have principally we have a very different picture. We have a branch cut which goes along all the real axis, and there is no analyticity domain here, and we cannot locate this ellipse. For this reason, scattering of massless particles and especially gravitons should be considered in a different way. So after this comment, I have some time to introduce another nice application of unitarity and of partial wave unitarity for computing loop diagrams, not loop diagrams, but loop contributions to the amplitude from their three-level contributions. And in general, the very idea that the amplitude can be reconstructed in the non-perturbative regime with the use of also, in addition, partial wave unitarity. So let me consider a very simple scalar, shift symmetric scalar amplitude. I even don't need to write theory in this case. As we saw, it was a good one-to-one correspondence. So I start from the amplitude of this form. This is three-level scattering amplitude. The question is whether what is the form of loop corrections, of at least one loop correction to this amplitude. Apparently, we can compute it without the use of Feynman diagrams. We need just the amplitude and the unitarity condition. Why at all we need to have, why at all loops cannot be equal to 0? The reason is partial wave unitarity, basically, because having this amplitude, in principle, we can compute its partial wave expansion, FL of S. It reduces to evaluation of the integral from -1 to 1 dx PL of x, and the amplitude as a function of S and T du can be written in this form. This is here I just do some trivial redefinition of the variable in the integral. Go from cosine theta to some abstract variable x and amplitude in this form. So in this way I can obtain partial waves, and after obtaining them I can apply partial wave unitarity. Precisely for this amplitude I have done it on Mathematica. It's some trivial computation. The result is for partial wave number 0, I get this contribution. And for second partial wave number 1 is 0 because of symmetry. Partial wave number 2 is alpha squared over 240 pi minus beta s cubed over 480 pi. So these are partial waves of three-level amplitudes. There is no imaginary part. But from the unitarity condition, we know that for massless case, it will be written as two imaginary part of FL should be larger or equal to modulus of FL squared. You see here there is some discrepancy. There is no imaginary part and no discontinuity in the amplitude. It contradicts to partial wave unitarity, to optical theorem, basically. It cannot be like this. We need corrections. We need loop corrections. And apparently, at the level of since we have the first correction, the first contribution to the partial wave behaves as S squared, modulus f0 squared will be 25 alpha squared s to 4 over 48 pi squared. And we know that this should be also, the two imaginary part of FL should be larger or equal to this F0, which means that there should be the running of coefficient gamma. Gamma should receive log running, some contribution like s squared log s, very schematically, s to 4 log s. I guess it's just looking at the partial wave. Then in principle, I can find beta function of coefficient gamma simply from partial wave unitarity. This condition will be saturated at this level because we don't have, because up to s to 6 terms, we have only 2 to 2 scattering. There are no contributions. Just by power counting, one can conclude that there are no contributions from 2 to 3 or whatever, 2 to 4, in neither in loops or in tree level. We have only 2 to 2, and we can consider that unitarity of partial waves is saturated. So we have equality here. So simply by optical theorem, we can restore the running of one of the Wilson coefficients. Even without looking at the Lagrangian, deriving Feynman rules, whatever, we can simply derive it from the amplitude and get the correct result. So the technique here is that I found imaginary part, found two imaginary parts here, but then I need to figure out what is the form of, what is the ansatz for the amplitude for the term, for this term standing with gamma. I need some ansatz, and I need to match coefficient of log running to alpha squared. And by the way, since we have s squared as a first contribution here, we don't get running of beta. So beta doesn't run, and alpha also doesn't run in this theory. The running starts from the coefficient gamma, and we can find it because imaginary part of A given in the form A1 s squared multiplied by s squared plus A2 tu. I can take this ansatz for imaginary part of the amplitude, then plug it into partial wave computations, and then find some conditions which are which can be solved as A1 is equal to 7 alpha squared over 320 pi, and A2 should be minus 1 over 21. This perfectly fits with the results given by computation of one loop in this, by direct computation. So I can find an ansatz for imaginary part of the amplitude, but then by analyticity, I can also find the whole amplitude, having its imaginary part. So A1 loop, how can I reconstruct it? I don't have much freedom to write much about this. So I need to have this term s squared minus 1/2. I put here log of s, and this will already give me the desired imaginary part, the desired discontinuity. In principle, I can have, then I have, I need to add cross terms. S exchanged with t and s plus s exchanged with u. This will give me log t and log u. But when s is positive and in the physical domain, s is positive, t is negative, and u is also negative. In log has a discontinuity only when log is positive. And also I take the branch of the log defined by the condition log s minus log minus s equal to pi I. It reproduces correctly positive imaginary part for me. So I guessed about the form of imaginary part with two arbitrary coefficients. I matched these coefficients to the condition of partial wave unitarity, and then I restored by analyticity one loop amplitude with logs reproduced in the correct pieces of the amplitude. This way I got the full result in a very short time, simply by taking some certain integrals with Legendre polynomials. This technique has many common things with the so-called S-matrix bootstrap program. The very idea of this program is that we may want to obtain the whole amplitude from, we might start from some effective field theory amplitude and then promote it to some unitary and having other nice analytic properties, non-perturbative ultraviolet amplitude, having nothing else at hand. And once we put this once we want to solve this problem, we use partial wave unitarity, analyticity of the amplitudes, and in certain cases, the result can be obtained numerically, but apparently it's not an exact result. It's since in general we don't have equality here. So if we have equality here, we can simply reproduce one by one the result, the non-perturbative result for the amplitude, starting from some tree-level seed amplitude. But in general, we have also processes like 2 to 4 and more, which will contribute in higher order in S, and in general, they will contribute. But this technique allows to construct certain boundaries in the parameters of the field theory space, where the good enough theories leave some compact boundaries in terms of both Wilson coefficients and construction of UV completion. And if the theory lives on this boundary, which could be this boundary, for example, where this condition is saturated, then we can find out what is the non-perturbative amplitude, having all these properties. But otherwise, it lives inside the boundary. We cannot define what exactly is the amplitude, but we can specify what is the range of allowed series, allowed effective field series, and allowed non-perturbative ultraviolet amplitudes. That's approximately what people doing numerical S-matrix bootstrap program, that's what they are working on. And the example I have shown is just a very simple application of the similar ideas to effective field theory, like a quick computation of one loop correction instead of dealing with many diagrams. In principle, in this kind of theory, even two loops can be computed this way. Not for all terms, but for the beginning, like up to S to 6, we can compute up to 2 loop corrections. There are results in the literature which are done for this kind of theories.
Then the imaginary part to reconstruct the total amplitude. That's what you're doing.
You mean here?
Yeah.
I'm just using the knowledge that if the amplitude is polynomially bounded in total, the only possibility to have constant discontinuity is to have a logarithm. I don't have other functions which have constant discontinuity and which are bounded polynomially. If I skip polynomial boundedness, I have more freedom, of course. I can like integral exponent or so on. We were playing a bit with this, but in
large S.
Well, here I have to do it. Yeah, this will be for large S, but since we are considering that UV completion of the theory is also kind of local theory, we want it to be bounded polynomially. So I'm just using the fact that there is only log properly bounded such that the discontinuity is constant. I can reconstruct this log from analyticity in principle.
Can you get this in some alternative calculation? You know, for instance,
You mean this amplitude? I think the same result was obtained by direct loop computation. Yeah. By direct loop computation in the theory. You can write Lagrangian and can write one loop. Yes. Well, not me, but in the literature there are claims that this results fits. I haven't done the whole procedure, but it seems to be straightforward.
this is for graviton amplitude.
No, this is for scalar amplitude, just the simplest case. For graviton amplitude, it's a bit more complicated because of basically this either a squared over t term, which appears or like the structure of SU plus ST over U plus T over S. So this structure is not very good for expansion in partial waves, especially in 4 dimensions. Because if you expand 1 over t in partial waves, you get infinity, 1 over d minus 4 singularity. So theories with gravity in 4 dimensions, they need some special treatment. The partial wave unitarity doesn't work well for them. The reason is that it is likely to produce a lot of soft gravitons instead of having 2-to-2 dominated scattering.
Then this will be the amplitude for dilaton, for instance.
Yeah, for dilaton it could be, yes.
Can you get that from string theory, this behavior?
Well, I think, I don't know what is, you mean I can try to apply this to one loop, to 3-level string amplitude and get one loop string amplitude. I don't know if it was done somewhere. This technique, I saw it only applied to photon EFT actually, and as quite a recent application. And also a few years ago, it was applied to getting pion scattering. It's just very convenient trick to get to loop pion Lagrangian scattering.
Example where this technique was matched to a CK calculation. There's a paper a few years ago by Andrea Guarnieri collaborators where they use this technique in 10-dimensional vector solution, and the one current contribution matched with one computed by Greenbaum.
Well, thank you for your comment, because I was not familiar with this. But basically, I think Andrea Guerrieri was also participating in some papers where it was applied to field theories. Okay, I think there are 5 minutes left, and I can more or less finished for today, and we can just have some free discussion questions.